For the obstacle avoidance part of our code, we start off by scanning for an object right ahead of us. If we have an object between 0 to 20 centimeters, then we'll stop, move backward for 1 second, and then we'll either turn left or right for 2 seconds. And if we have an object between 20 to 50 centimeters, we'll reduce the speed of our car to 10. Otherwise, we'll just move at a constant speed of 50. So now I'm going to be walking you guys through the object detection part of our smart car, which is inside the smartmovements.py script. So essentially when we run it, it will run a main thread, and then it will instantiate all the global variables and the threading events object from Python, and it will start the vision thread. The vision thread itself is a thread that we use so that we can simultaneously scan for a stop sign while moving our smart car. So after that, the main thread will go to the movement routine, where it will just see if the stop sign is detected. If not, then we'll move forward 4.1 millisecond, and then it will constantly check for the stop sign if it's detected. And if it detects a stop sign, then we'll do the stop sign move sequence, which is a visible, very unique pattern of movement sequence that we do, so we can visually confirm like if the robot has detected a stop sign on the field, and then it will check for another stop sign essentially. And for the vision thread, it will constantly scan for stop sign, and then if it detects a stop sign, it will change the flag for a stop sign detected, so that the movement thread can go to the stop sign move sequence, and then it will reset the flag after all the movement sequence is done, so that the vision thread will know when it's time to start again. This is done so that the scanner doesn't scan for stop signs when we're doing our stop sign move sequence related to the previous stop sign that we detected. Okay, so now we're going to be walking you guys through the code itself. Here we have the smart movements PY, and when we run it, it will instantiate the stop sign detected, which is essentially a threading event object from Python, and it will create a vision thread, and then it will go to the movement routine. Movement routine itself is simple. It's a while loop. It checks if a stop sign is detected. If not, it will move forward 4.1 millisecond. If it detects a stop sign, it will do a very specific stop sign move, and then it will modify all of the relevant flags to let the vision thread knows that it's time to scan again. So here's our stop sign move. Essentially, it stops for 0.5 seconds. It would squiggle back and forth, and it stops for 2 seconds, and then it will turn left. For vision itself, it will constantly check for stop sign by calling this method scan stop sign, and if it does, it will modify all the relevant flags. And for the vision object itself, it is an object from the detect Pi camera. So over here, from the detect Pi camera script. This script, we got it from the tutorial page for Raspberry Pi for object classification on the TensorFlow website. We modified it so that we only focus on the stop sign detection. But essentially, when we instantiate the vision class, it will set up the interpreter, it will set up the camera, and then when we scan for stop sign, it will run like a continuous stream, and then we'll just try to detect for a stop sign on the images. And if it does detect a stop sign, it will return true. We do this by essentially checking for the objects itself, if it passes the threshold in terms of the confidence score, and then if it matches the stop sign ID. And if so, it will return true, and then it will let the smart movements part of our code know that we have detected a stop sign. Yield, do nothing, stop sign. Okay, acknowledge, turn left. There's another stop sign over there. It should see it, it should acknowledge it, and now it's gonna turn left.
Perfect turn.
Perfect turn right there. We have another stop sign over there. Yeah. There you go. Acknowledge, turn left.
Hey everyone. So before I get into the implementation of our advanced environment data structure, I just want to visualize how it actually looks like. So we chose to use a 2D NumPy grid with a couple of parameters, which are the granularity measured in centimeters, which is the size of each tiny square of the grid, and the side length, which is the length of the side of the grid. The grid is a square, and there's also vision distance, which is the distance from the pi car to which the pi car is gonna add obstacles in the grid. So anything beyond this distance is not going to be added. And I also want to show you guys the coordinate system that we chose. So the origin is actually at the top left instead of the center, and the y increases downwards and x increases rightwards, and the angle increases counterclockwise and decreases clockwise, I think. Yeah. So yeah, let's get into the implementation. So there are two classes that come into play with the advanced environment mapping, which are environment grid and smart control. Environment grid is the class that keeps track of all the position and orientation, all of those variables, whereas the smart control is the one that takes input from the user and from the car and modifies the data inside the environment grid. So environment grid class is more like a storage unit, whereas the smart control is the thing that actually does all the controlling. So here we have like a simple initialize method with the granularity, side length. Here we are centering the here's the position of the robot X and robot Y, put in the middle of our grid. Here we just return the position. This is the method that updates the current position and the current orientation of the object of our robot. We pretty much do a simple geometric calculation to I'll show you the update position. So yeah, here's update position. If it's moving forward, that means like if the robot is like moving forward, we update the position, which calls this function get position, which pretty much does a conversion from polar coordinates to Cartesian coordinates, and turning left just multiplies an angle by this turning speed. So it's a very simple calculation. Process can output. What this does is it takes in an array of pairs, an array of pairs. The pair has an angle and a distance, so it pretty much measures the distance at each angle, and then records if there's an obstacle. So that's like yeah, and if it's less than the view distance, then it will get recorded. If it's more than the view distance, it will not get recorded. And what else? This is a simple function that checks if a cell is valid so that we don't end up causing an exception. This is the function that records an obstacle. It pretty much sets the map from a 0 to a 1. And this is what maps an XY position in centimeters into an index of the map. So going quickly through the smart control, the interesting part that's relevant to us is here. When we press W, we update our current position, or any of the keys. We update of our current position, and we record our orientation, current position, and average speed. And the way we calculate our current position, it involves looking at our previous position and our move state. So let me go through that quickly so that it's a bit more clear. So over here, the way it works is we check the last log, and then if we have been moving, we take that into account and we calculate our position accordingly. If we have not been moving, then there's no update happening. And we're also logging with each movement so that the calculation gets done properly. And yeah, so this is what these are the keys that get activated whenever the player uses the keyboard.
The text is
Here's the
surrounding, the
wall.
text, the wall,
Here's
the clearing.
the clearing.
Okay, that's good.